Hello and welcome to problem 4-9. So in this exercise we will be considering what we call a zero modified distribution, which is actually extremely interesting from a non-life insurance point of view. So let's just try and look at the setup here. We consider a stochastic variable m, which we use to count things. So m can be either 0 or 1 or 2 or 3, so it can take on any non-negative integer value, each with the point probability p0, p1, p2, p3, and so on. So with the fancy notation, what we write is that the probability of m being any non-negative integer n is given by its point probability for n going from 0, 1, 2, and so on. So just note that the pn's here are not specified, but what we write here is just that we use pn as the symbol for the point probability in n. Then we're asked to look at the so-called zero modified version of m. There are certain different terms that we also use in the literature. Some people say zero modified, some people like to say zero inflated. And the reason why we use the term inflated, you will understand just in a second. So the zero inflated version of m is introduced as the stochastic variable n given as the product of a 0, 1 variable I with m, where it is assumed that first of all, I is Bernoulli distributed with success parameter p, so that means that I is equal to 1 with probability p, and it's equal to 0 otherwise, so with probability 1 minus p, so that's what we get from this thing here. And also we assume that I and m are independent. And as soon as we see that I and m are independent, we remember all the things that have to do with independence between two stochastic variables. That means the product of these two, if you take the expected value, then you can split up the expected value into a product of expected values, and so on and so on. So in this exercise, what we're asked to do is we're asked to calculate the moments of the zero modified version of m, and we're asked to calculate the point probabilities of the zero modified version of m. And also, assuming that m is a Poisson distribution, then we need to show that the zero modified version, or that m is Poisson distributed, then we need to show that the zero modified version of m is over dispersed, which means we have to show that its variance is strictly greater than its mean value. Now, before we get started, let's just recall a few results that we have about independent stochastic variables. So first and foremost, note that if we have two stochastic variables that are independent, so if x and y are independent, then a function of x will also be independent with any function of y. And also, if x and y are independent, then recall that the mean value of their product can be split up into the mean of each of them multiplied together. Now this follows quite readily from the definition of covariance, but I don't know if you guys have seen the proof for that. Well, anyways, so this will probably come in handy when we need to calculate the mean of, when we need to calculate the kth moments of n, and also the definition of the variance of some stochastic variable is always equal to the second moment minus the square of the first moment. So we need that, and I guess we'll just kind of improvise for the rest. So before we start doing the solutions, I would really like to recommend the next video for you guys in order to understand the intuition that lies behind this exercise and the motivation behind making zero inflated versions of counting distributions. So take a look at the next video. I will tell you some stuff that we haven't talked about in class, and probably it will also motivate you guys to think that non-life insurance is pretty damn cool.